Asymmetric cryptography can be used for encryption, as we have seen. Has been used for encryption, as we have seen, and can also be used in a complementary way for authentication. This is called digital signature. How does digital signature work? It's very similar to the MAC that we've seen a minute ago, but now with the twist that we have a public and a private key pair. With a digital signature, if you want to authenticate a message, you sign it with a private key. You send it through the channel. An attacker can see it. The goal here is not to have confidentiality. And the verification will use your public key. So it's the converse of confidentiality. If this scheme works, anybody can have the public key. But of course, the private key should be held only by this device. If this is the private key of the PMU, only the PMU may have sent the message, but anybody can verify it. Other than that, other than this asymmetry, the requirements are very similar to the ones we had for MACs, which used a secret key. Except now the fact that the public key is public provides a stronger guarantee. In particular, if we are certain that the public key is from this guy, anybody can verify that this message was signed by the owner of this private key. So we have what is called public verification. So anybody can verify that it was signed, but anybody can also know that it was done by this one, not just the intended receiver. So everybody can know that you had received a message signed by someone here. It can also be used to provide what is called non-repudiation. M cannot say that it did not sign the message, at least as long as we believe cryptography works, because the only one who has a private key is M, so everybody can see the message, everybody can verify it, so the public knows that M sent this message. With private key cryptography, we could not make those things public because the keys are supposed to be secret here. But here the public key gives a stronger property, which is non-repudiation, which is of course very useful. If you buy things over the internet, you want to make sure that the transaction occurred and that you agreed to sell, for example, or that the seller was agreeing to deliver you something. How does it work? Well, with RSA, it turns out that you don't need another scheme to make that work. It's the same encryption. The same method we saw for encryption works also in the other way around because of some commutativity property. If I call D the decryption operation and E the encryption operation, I encrypt with a public key and I decrypt with a private key, then the correctness of any encryption scheme means that the combination of those two operations, first encrypt, then decrypt, is the identity. I received the message that was originally sent. Well, it turns out that for RSA, like with DSA, the maths of the encryption are such that those two operations commute. So if I do first the encryption, then the decryption, like intended here, or the other way around, if I first apply this operation, which is now the same one, I cannot really call it a decryption because we're not decrypting something that was encrypted, but mathematically the same operation. If I do it first, then by applying the encryption, the same operation that was done by the encryptor here with the public key, will provide the original message. This is because those are all exponentiations, and m to the power e to the power f is the same as m to the power f to the power e. So how can we use that for signature? Well, if I have to sign a message, I will apply this operation, which consists in computing it to the power f modulo k, where f is a secret. F, remember, was this derived from the secret key of RSA. Of course, you keep it secret. This is what we use for decryption, except here we don't decrypt anything. We just compute this to the power f, and we send it in the clear. Now, to verify it, then we apply the encryption operation, E capital K, which consists in computing this to the power E. So the verification, the tag here, S, which is now called the signature, to the power E. E is public, that's one of the constants of the scheme. Modulo K, K is the public key, which is also known. That should give exactly M, the original message here. So that's the first principle. Except here, what I do is if I apply that to M, here that's still, if I receive the message M, the signature S, by complying S prime, I should obtain the same as the original one, and if so, the thing was not tampered with. In practice, however, what we do is we want a tag, so something that is not as long as the original message. So in practice, what is done is to compress the message before applying the signature. This compressed thing is called a digest. So we have lots of things that look very similar. The tag, the digest, and the signature. The signature is equivalent to a tag when we use asymmetric key cryptography. Except here we call signature. And the digest is a bit different. The digest is something that is constructed from a long message by applying a hash function. What is a hash function? Hash function is something that's used everywhere in computer science. If you use Python programming, for example, you will have dictionaries that can use hash. So a hash function is anything that maps a message of any length to a short block of k bits, where k is specified, which is called the digest. And to qualify as a hash, it must have the property that the digest to be chosen at random. Of course, it is not random, it's completely deterministic. If I give you a message and I hash it, D depends deterministically on M. But if you have many, many possible messages, and you look at the distribution of the digests that are obtained, they appear to be uniformly distributed. They appear to be random. Like Homer's function that we saw last week, the Homer's MAC function used secret keys. A hash here doesn't use secret keys, but if we make the secret key public, that would be a hash. It transforms a text of any size into something modulo some number, and it will appear uniform. In fact, if you take a long message and you translate it into a number by applying a mapping table, a known public mapping table, for example, the ASCII table, and if you take the remainder modulo 257, for example, it will appear to be any number chosen uniformly between 0 and 256. That is what is called a hash function. This is used in computer science to reduce the set of lookup tables. If you have a huge dictionary with 40,000 words, for example, then if you want to search for a word in the dictionary, one technique consists in first hashing the words and with a hash that would be much smaller, for example, 16 bits, and then look first for the corresponding hash value. There will be a small number of words that will correspond to the same hash value, and if your hashing is uniform, for every hash value there will be, roughly speaking, the same number of original words that will correspond to the same hash value by the uniformity property. So that you will divide something that was a big operation, finding among all the possible words where is yours. Instead of that, you can first search for a hash value, and then among all the hash, find which one is your word. You can also hash and hash again. In computer science, as you should know by now, most of computer science is about transforming a very complex problem into a problem that's a bit less complex, and then we will apply it many times, and at the end, we'll have something simple. This is how computers work, right? They do additions and multiplications, and that's all, and they can do all the beautiful and ugly things that we know of them. So that's the hash function. Of course, so a first thing to remember, a hash is very similar to a MAC. A MAC does that also, but a MAC has a secret key. A hash does not have a key. everybody can compute the hash and everybody can verify that this thing is the hash of the thing that you get. The idea of a signature is that we apply the hash first and then we sign the hash with a signature, as I've shown before, in order to have a signature that applies only to a hash which is a smaller number. Because remember, otherwise, a signature scheme like RSA is like a block scheme. It will be as long as the original, so the digest will have the same size as the signature. I mentioned Homer's function. Here it is, the same as before, where I put the numbers A and B public, and we do the modulo 257. If you take any text and you apply this, you will obtain something that appears to be random. In fact, some random number generators used for simulation use similar things, with numbers A, B, and P that are larger, but using the same principle. So here I would use this large text into this small hash here. And if I change anything here, for example, if I change the bank account number, like we said before, the hash value will be 74, which was not the same as F7. So if the hash is good, if it's cryptographically secure, then it should be very difficult to forge the text to obtain exactly the same hash as before. This hash is not secure because I managed to change the text here such that I obtain the same F7, which is the same as before. What did I do here? I changed the number here so that the money goes to me instead of to the intended recipient, which of course will change the hash here. But then I introduced other changes in the message that will correct the same hash here. What changes did I add? What did I do to the message?
Add some space.
I added some space, right? I added blank space here, which still will look a bit weird, but you might think, well, that's how the system works. This is the message here. If you send that to a human being, you will believe it's the same message. So here I managed to do an attack on this hashing function, hashing system. I transformed the message intentionally, and then I added some transformations that appear to be not changing the semantic of the text, but that corrected the hash, the errors I did in the hash. That's possible because the hash function is done by simple linear modulo 257 arithmetic. So if I know what is the ASCII code, of a blank space, I can compute how many blank space I need to add such that the difference between the hash and the intended hash is exactly the one I wanted, which I did here. So that is an example of non-collision resistance. A good hash system should not allow to perform this, should not be able to create two hashes. Because no matter how strong my RSA will be, when I will compute the signature, I will compute the signature of the hash. So if I sign this message here, it will be correctly signed. If I send this message, if I send this message plus its signature, the signature that was computed only on F7 will not change. Of course, in reality, we don't use 2 hexadecimal digits, which would be 8 bits here. It's an 8-bit hash, which obviously is too small, but we would use a hash that's much larger. But still, the problem remains. We should have, like for tags, we should have the impossibility, practical impossibility, other than by brute force, to create such a collision. But here, of course, we don't have a key. So the hash must be much stronger, because if we had before, the attacker's job was more difficult because the attacker had to solve the problem for my key, for every key. Whereas the hash here doesn't have a key. So an attacker can put all their resources into attacking this hash function. And this happened in the past. In fact, this is one of the big weaknesses of digital signature schemes, in that the hash function must be cryptographically secure, which means it must be practically impossible to do the attack I showed, to forge a hash that corresponds to a forged text. and previously used hash like MD5 or SHA-0 were broken. So by similar reasons, they were more or less similar to that thing, but with more tricky things, but with a bit of advanced mathematics, you could find a way to do what I did here using elementary modulo computation that was done to this here. So again, that's the message I'm repeating again and again. Security is good as long as it's not proven to be bad. So make sure you have up-to-date software that uses, for example, SHA-2. Those are two. SHA means hash, right, in the reverse. Secure hash function. SHA-2 or SHA-3 are considered to be secure today. Many attacks consist in detecting whether a system has old software. For example, if you have MD5, it's known, and now that the math is known, fairly easy to attack. So this attack that I showed of sending a wrong message is very easy to do. I mean, you can do it easily if the attack system uses MD5. Now, MD5 was considered secure 10 years ago. If some system has not been patched for 10 years, probably it is using MD5. So it can be attacked. That's the bad news about security, but we have to know it. Back to speak up. I close in 5 seconds. And by a short majority, the class is right. So the correct answer is PMU's public key. PMU will sign the message with its private key. Of course, if it would sign with its public key, anybody could sign it. So it will sign it with its private key, and to verify it, you verify with its public key. Anybody can verify. Only the owner of the private key should be able to sign. Otherwise, it's not a signature. More tricky one. When you will read security software, you will see things like this. Right? We've seen CBC AES, that's an example. HMAC SHA, that's an example of asymmetric authentication that uses a key and creates an HMAC, which is the result of applying asymmetric cryptography-based signature to a hash. And SHA is 256, means it's a hash, where the key is of size 256, with the hash is of size 256, and because it's a pure hash, it does not have a key. Here there is a key, but the key is because of the HMAC that we use here. So what statements are true about all those systems? close in 5 seconds. And the majority says D, but the correct answer is none. None of them here. So of course, the statement means if two ciphertexts are the same, then it must mean that so this is a symmetric crypto. If two ciphertexts are the same, does it mean that the clear texts are the same? Well, no, because there's a key in between, of course. So for different, if they have, they have the same here. So yeah, so this is correct. This is a typo. I forgot the key prime here. So those are, then this is correct. A is correct. So if C and C primes are the same, if you encrypt two messages with the same key, then of course the two messages should be the same. Otherwise that means you cannot decrypt. Right? If they have the same key, somebody who has the key will read M from C. Somebody who has the key will read M prime for C. Therefore they will be the same. So A is correct. B. Now B, there is a subtle thing. No, they have the same key also. So this is now, this is a tag. So this is used for verification, for authentication on. If two tags are the same, does it mean that the messages are the same? The answer is no. Although it's very hard to create a collision, but the tag is smaller than the entire message. So by the principle of what? Of pigeonholes. If you have more pigeons than holes, you must have at least two pigeons in the same hole. Right? If you have more messages than tags, there must be at least two messages that have the same tag. If they're encrypted with the same key, it doesn't change. So, but of course, if the tag is length is long enough, it is practically very difficult to create a long message that has the content you want and that has exactly the same tag. But it is not true here. D is a hash, so hash is the same except there's no key. So the same happens. The hash reduces the size of the message. So two hash may collide, but of course it's very hard to forge a collision. So the correct answer is A, which was chosen by no one. Question. Why B is not correct? Because this is not an encryption, but just a signature. So first we hash the message, then we encrypt the hash, so that's a verification scheme. But because of the hashing, we've reduced the size of the message. So if your message is 20 pages long, you reduce to a tag of 1 page, then of course there must be there can exist two messages of 20 pages that result in the same. Again, which one, I don't know. It's a theoretical result that says there can be there must be two messages, but that's the pigeonhole principle. If you map a large set into a smaller set, there must be at least two elements that are mapped to the same thing. You cannot have a one-to-one mapping. The one-to-one mapping can only be done into a set that is at least as large as the original set. That's set theory 101. Okay. This is what we can do with the digital signatures that are therefore very similar to tags. Now let's look at another problem. Lisa goes to her bank, gets the public key of the bank, will create two session keys, one for encryption, one for verification, and then the transactions can happen happily with the bank. This is what we saw. It's typically used. This is called hybrid cryptography, and that's the standard, one of the standard uses of combination with symmetric cryptography. But now assume somebody does a man-in-the-middle attack. like we do in Lab 2 for the advanced users of this group. So it's very easy to break a connection and read the traffic that goes into it. This is why we should use cryptography so that if you read something, you don't get any information out of it. But here, assume the bad guy here, that knows, of course, the public key of the bank, replaces it, so intercepts the message. The public key is, of course, in the clear, and sends its own public key. Right. Rogue bank. Then Lisa will happily encrypt everything, but will talk to the bad guy. Now the bad guy will talk to the bank here and will create other, will first decrypt everything that has to be decrypted from Lisa, will re-encrypt it and send it to the bank, and therefore will be able to change all the messages here. So this is called a man-in-the-middle attack. He has obtained the secret session keys because he fooled Lisa to believe that he was the bank. So Lisa sends something that's secret to Lisa and what Lisa believes to be the bank, but in reality is the attacker. Right. So the secret key is known to here. And the bank believes she's talking to Lisa, but she's in reality talking to the attacker. So that's called a man-in-the-middle attack. When we reason about security, that's one of the major attacks that we could imagine can always happen. When we send something, we should always imagine there is an active attacker in the middle that is able to forge any message we send here, including the public key here, if we get the public key from the bank. So the problem is because Lisa was assuming the public key she sees on the site of the bank is the bank's public key. Then we have a problem because the goal of public key encryption was to distribute the keys, avoid the problem of distributing the secret keys. But now we have the problem of distributing the public keys. So we have a chicken and egg problem that we will solve like all chicken and egg problem by making sure the first hen is producing a correct egg. Right. And all the others will be correct. Here, in this context, this is called digital certificates. So digital certificates rely on the idea that there are trusted entities, like VeriSign or GlobalSign, that have public key let's start with that. So the certificate authorities will contain a text that certifies that the public key is really that of the bank and not of somebody that pretends to be the bank. So for example, in Switzerland, you require that the bank is officially registered as a bank. For example, Banque Cantonale Bernoise is registered here, Registre du Commerce Bernois, has a number, and will verify this entity, GlobalSign, will verify that the guy who comes looks like a banker, but is really a banker and has the authority to say, I speak in the name of this bank. And here is the public key, and therefore this must be the public key of the bank. Now, the certification authority will sign the public key with its own private key. It will sign this entire text, which is called the certificate. It will sign, in particular, the description of the bank and the public key of the bank here. This is called an identity certificate. Now, if Lisa has this certificate, whenever she receives something from the bank, she will receive a certificate, not just a public key, and the public key is signed by GlobalSign, and Lisa or her software must have, of course, the public key of GlobalSign. Typically, it is pre-installed in browser or in PMU software. So, operating system software, usually if you buy a Windows PC or a Mac, or if you download something from Linux, then you need to be more careful. You must make sure that the operating system software installation that you're doing is correct, because it will contain things like this. It will contain public keys of certification authorities. So if you buy a computer that is pre-installed, you trust that the shop that is selling you the pre-installed Windows has not tampered with it. Right? If you get it from anywhere, if you get an image of a version of Windows of 10 years ago because you want to crack a game that worked only on Windows 2000, probably this image is corrupted, and because that's a very classical attack vector, we consider distributing operating system versions that are corrupted by wrong public keys. So that you will go to obscure, instead of global sign, you will go to global sign that will be under the control of whoever wants to attack, whatever organization is distributing this software. So that's one of the very critical things. The software that you install for the first time when you boot a machine, this one is very critical. If you can trust this software, you can trust the rest. If you cannot trust the software, you don't know what you're doing really. And if you get the software from a non-trusted source, chances are it will be corrupted. So Lisa is using, I don't know here, perhaps Windows, or when you have Windows, you get probably Microsoft Explorer or Edge that you can use then to download Chrome, but then you must make sure that you get from Chrome, that you are really from the website that is allowed to distribute Chrome, which is typically Google, which is the same problem as going to the bank. So the problem is how to bootstrap trust, and you do that by the first software you install on your machine. From there, you use certificates. For example, here, Lisa, when she now talks to the bank, she gets a public key through a certificate from the bank, and she can verify by using the public key of global sign that this is indeed the correct public key of the bank. And therefore, when she will send everything to the bank, the man in the middle she will sign it, she will use the public key here to encrypt everything, and then the man in the middle, who does not have the private key, will not be able to decrypt it. The man in the middle has his own private key that is hopefully not signed by a certificate. Certificates, like everything, have a validity time because it can happen that private key has been corrupted, a bank had a problem, or the software was corrupted or was victim of an attack. So certificates themselves have a validity time, which means that we depend on time in the computer. Right? If your computer believes we are in 2010 because your clock is incorrect, it might accept a certificate that is valid until 2011 that was using, for example, a form of RSA that uses key of only 1512 bits that we know now how to crack, instead of keys of 2000 bits that we don't know how to crack today. So your computer will happily accept things that are invalid today, but that were valid 8 years ago. So you must also have a correct clock on your computers, on your PMUs, on everything. You must have correct time. For PMUs, we know we must have correct time for other reasons, right? For what reasons do we need correct time on PMUs?
Synchronization.
Synchronization, yeah. Having the correct time is called synchronization. So why do we need synchronization? Well, you measure phasor angles, right? The angle is with respect to a time. So if time zero is here, your phasor is here, your phasor is zero. But if time zero is there, and your phasor is here, your phasor will be 45 degrees instead of 0 degrees. So the measurement of an angle is a phase with respect to time. You need to know what is time zero. Also, you need to time align. You need to make sure that the different measurements are taken at exactly the same time. So PMUs have a very strong time synchronization, so it's not a problem. But you might have other devices that people don't think they really need time. Why do I need a clock in, I don't know, a smart meter controller of some kind? That is the kind of things you must think about. What do you think that a certificate should contain? CA stands for Certification Authority. I close in 5 seconds. And the majority says G, but, well, it might be true, but if the certificate contains C, probably I should not use it. Because a certificate should contain the public key of the bank, the identity, so that we check that the public key is in reality this and this one, and of course a signature. But the public key of the issuing certification authority will be used for verifying the signature. So if you put the public key in the certificate, I mean, anybody can do a certificate. It can be the bad guy that is sending the certificate to you, if you're allowed to put this here. So I'm not saying it is not present in the certificate, but if it is there, it is information that we should not use. The public key of the certificate should be known from a trusted source in your device, which may be the original software that you've installed, or software, additional software like Chrome, an additional web browser, that was installed in a secure way. So it's very subtle, it's very easy to attack systems, and one of the attacks consists in replacing certificates by what is called self-signed certificates. The self-signed certificate is what an attacker does. It says, I am the verifier, I signed the certificate, and here is the proof, because you have the public key, you can verify my signature. Of course, you can verify my signature, but you don't know who me is. So this is not working. So the correct answer, or at least the information we should use, should be A and B. If a certificate sends this information, it's either stupid or trying to mislead us. How comes this was... Okay, we're almost finished now in all the elements of security that constitute the state of the art today in terms of cryptographic means. The last one is forward secrecy, and this is what we will conclude with. With all the mechanisms we've seen, if we use certificates the right way, we're able to talk to sites, make sure this is really the site that we're talking to, therefore use the public key to establish secret keys that will allow us to be confidential and to authenticate everything. However, things in computer science are moving. What is secret today might be possible to attack in some years in the future. So if we apply this by looking back to the past, we can say that some things that were secure 5 years ago are perhaps not secure today. So it poses a problem that assume an adversary records all messages. So you have somebody that's sniffing your traffic, but you don't know. The attacks were not successful because you had strong authentication mechanisms. But assume that sometime later, the private key that was used at this time when we were doing this, the private key of the bank, for example, is revealed. Why would a private key be revealed? Is that a completely academic exercise, or do you think it might happen? Public key of 5 years ago. Well, there might have been an attack against the site. Right? Perhaps this is not the bank, because the banks are very, very, very careful, and they tend to prefer to kill the people than to give a secret. But companies like Google+, and the social network of Google, Dropbox, so big names, had attacks where some of the secrets were revealed, passwords in particular. So a password might be revealed, and if you're in the darknet, you will find the passwords of lots of people. Perhaps one of them is an employee of the bank, and then you can perhaps gain a secret of some. Perhaps also a computer was stolen somewhere, and the hard disk was analyzed, and perhaps today it's not possible to decrypt it, but perhaps in 5 years, when decryption technology has improved, perhaps it becomes possible. Or perhaps also this was using RSA with a small key that at that time was good enough, but today is no longer good enough. Well, this is what will happen when quantum computers come. All the things that are using RSA will be decrypted, so all the keys will be decrypted. And there are other attacks that are on RSA. For example, in RSA you have to choose prime numbers, random prime numbers to create, that's your secret key. Some people, like Marguerite, who was teaching you last week, has done some researches on finding whether pairs of prime numbers have been used, whether prime numbers have been used in more than one pair. And that happens. Some companies were a bit non-serious in their software, so instead of choosing two random prime numbers, they picked one always the same, and only the second one was random. But of course, once you know that, you can you can try to break it, and this can be broken. So there are lots of reasons that can make that happen. Of course, typically, what happens when such a security weakness is published, your key is too small or there's an attack, then you quickly fix it. But the things that were done were done. So what happens? If all the message exchanges were recorded, and now we know the secret key. Then if we have the log of all the encrypted messages and one of the private key, we can decrypt the log. Now you can tell me what's the value of decrypting the log. Doing a bank transfer, of course you cannot repeat the bank transfer now. If you just replay the message, it will not be useful. However, there might be confidential information in messages, like passwords, for example. You are logging to a site, typically you will use that kind of things before you reveal the password, hopefully. Not always. Sometimes you go to a merchant site, you say, I've lost my password, and they send it to you in an email, in clear text. If they do that, then it means this site is not very secure. So hopefully the password was sent only after this point here, encrypt message. For example, the password you sent to the bank to log in is sent only here. But now, if the attacker has the logs and the private key, he can find your password. If you're doing what I recommended to you, that's not bad, because you change your password every year and you use a different password for every site. But there are enough people who don't do that. So once you know the identity of a person and one password, you will very quickly try all the accounts where that person is susceptible to use that password, and that might work. Right? So if you hack a professor's password, perhaps you can change the grades at an exam, and then that's the kind of attacks that can be done. Avoiding that is called forward secrecy. Forward secrecy is a desirable property where we would be immune against that. Forward secrecy means that even if you have the logs and the private keys that were the permanent private keys that were used at that time, you cannot decrypt the logs. With the schemes we have given so far, it's not possible. With the scheme, the hybrid encryption scheme that we've seen here, if I know the private key here, if I recorded all of that, I can now decipher this message. Therefore, I will have L, and then if I have L, I can decipher all the next messages here. For that, there has been something that has been invented, which is called Diffie-Hellman key exchange, which is an alternative to creating a secret key. We have seen one method already with public key cryptography. I can create a secret key between two entities by choosing the key randomly and then encrypting with RSA. That's one way. But if the key, this is not forward secret, if the private key is lost. Here, the idea is, again, to use discrete logarithm, which is underlying much of the things we've seen. So there's another clever scheme which works as follows. You choose a random number between 1 and a maximum, which is very large. So this number n, which is very large and prime, has what is called a generator. So what is a generator? That's one thing of number theory that says that all the numbers between 1 and n minus 1 are a power modulo n of this. Here. If n is a prime number, there exists a generator. For example, modulo 257, there is a number g such that all numbers modulo 257 except 0 are g to the power something. as we saw, if we know G, if we know N, we know G as well. And given N, computing G to the power N is easy. It's not very difficult. We've discussed that already. However, it is believed that the reverse is difficult. Computing the exponent given N, which is called a logarithm. That's what we do when we compute the decimal logarithm, is finding x such that y is 10 to the power x. So it's exactly the same thing, except here it's a combinatorial problem. It's discrete things, and n again you have to think it as a very, very large number of the size that I showed 1 hour ago. This is believed to be very hard to do. So as long as this is hard to do, our system will work. The way it works, so you choose a number randomly, and then you send G to the A of this number. This is not your secret. This is just only half of your secret, or not half, it's just a number that we use to create a secret. The other side does the same, but probably will end up in another number B because it's chosen randomly, and sends only G to the power B. Then what I will do, I know A, which is my secret. I keep this secret, I will never send it to anyone. And then I compute what I've received to the power A, so GB to the power A. And the other side will do the same. And because there is commutativity of this, G to the power A to the power B is the same as G to the B to the power A, which is the same as G to the power AB. Therefore, the two entities will compute the same L without ever exchanging that. Same property as we saw before, but now there's no key. We don't need to know a key. Lisa doesn't need to know a key of the bank, and the bank doesn't need to know a key of Lisa to do this. So we have obtained a secret number, which is known only to the two of us, by using each of us a secret that is kept only with us. That's the principle here. For example, here, if n is equal to 17, which is of course not a cryptographically large enough number, if n is equal to 17, a generator is 3. You can verify this. If I compute all the powers of 3 modulo 17, the first one are easy. 3 to the power 1 is 3. 3 to the power 2 is 9. 3 to the power 3 is 27. 27 modulo 17 is 10. So 3 to the power 3 modulo 17 is 10. And if I continue with all the powers, I obtain all the numbers between 1 and 16. 17 would be equal to 0. 0 cannot be a power of something other than 0, so the 0 has to be excluded. And the discrete logarithm is the reverse mapping. For example, if I ask modulo 17, and when I pick the generator 3, there might be other generators, but there is always at least one, the exponent that corresponds to 11 is 7. So this 7 is the discrete log of 11. And if you look at things here, the order appears to be completely random, right? The discrete log of 6 is 15, the discrete log of 1 is 16, etc. A few discrete logs are easy to compute, but most of them are very hard. So it's believed to be a hard problem if the number is very large. I showed here a simple example where we do modulo 17. If we do modulo a huge number, that will be the same but more difficult. In practice, very often we use elliptic curve cryptography, which has a bit different computations than the modulo, but the principle is the same. For example, here, A picks 7, therefore sends 11 here. Computing 7 from 11 is believed to be a very difficult thing. So whoever sees 11 will need a huge amount of time to be able to obtain the 7, if this n is large enough. We send 12 here, and then when we compute 12 to the power 7, we obtain the same number as if we compute 11 to the power 13, which is in that case 7. So that's the principle. This doesn't yet solve the problem, because we have the same problem of the man-in-the-middle attack here. So this is man-in-the-middle attack here. Same problem as before. If the man in the middle chooses the secret and pretends to be Lisa to the bank here, both will agree on something, but the man in the middle will have all the means to decrypt everything and will, of course, be able to forge the messages. So this is fixed by having a use of keys here. So here's how it works. So first, we will we'll still use private and public key here. So we will do a key exchange that will be signed with one of the two private keys. So the random number A gives X, and then we will sign X with a key in both directions here. So we will need a private key of each, and then, only then, we will obtain the message here. Note here that we use the key only to verify, not to encrypt. So those things are completely public, so the attacker will have this. But here we are sure, at the time we do that, there is not a man-in-the-middle attack. And if later the secret keys are have become public, it doesn't matter because the verification is done in real time, it's done now, not 5 years later. Of course, all the material that is written here, A and L, or B and L, are temporary session keys, so they must be thrown away when a new session key is computed. Of course, if you have access to the disk and this would be stored in clear text in the disk, in the log, then you would be able to decrypt it. But hopefully your security software will not store on permanent storage the secret keys that are supposed to be secret and temporary. Then anybody who has access to the logs here, and even to the public and private keys here, will not be able to do the computation, at least as long as the discrete logarithm remains a hard problem. One more quiz. Last quiz of the day. Close in 10 seconds. I've lost the connection to the server. Start again. Close now if you had enough time. And the majority says C, which is correct. So with Diffie-Hellman key exchange, both parties can create the same secret without ever sending any secret information on the line. We have seen also that hybrid encryption does it. But this all relies on the discrete logarithm. So as long as this works, it's forward secret. If not, then it will not be forward secret. Voilà, that's the end of the lecture today. A bit early, but you have also a lot of lab material to do. We'll be happy to have more time to do. I hope you have gained the conviction that a cryptographic method that is secure today will not be so in the future. So perhaps that's the most important take-home message. I hope also that you have now a mental model of the basic encryption and authentication primitives are, symmetric or asymmetric. We've covered all of them. And the last thing I hope to have convinced you of is that this is as secure as we believe it is, but security is not mathematically proven. Right? If you use all the top-notch security, but you put your password on a post-it on your screen, right, then your system will not be secure. Right? Voila, that's all for today. We meet again on Friday for a test on this. At the beginning of the lab session, we'll do a test on this part, on the advanced or beginner's part, depending which group you're in. Merci.